One of the biggest problems we face when travelling in space is the atrophy our bodies endure while in microgravity. The astronauts on the International Space Station have to exercise several times a day to maintain their bone and muscle strength. But is there an alternative? Can we create artificial gravity? I'm sure you've seen the idea before in movies like 2001, A Space Odyssey, where the entire space station spins to create artificial gravity. The people inside can now walk comfortably, just like they do on Earth. It does this by exploiting centrifugal force. Now it seems that whenever someone mentions centrifugal force, angry mobs will show up in the comment section declaring it isn't real, which just isn't the case. Let's see why. NASA developed this huge centrifuge to test the possibility of simulated gravity back in the 1960s. Here we're looking from an inertial frame of reference. That just means we're looking from an outside perspective, and we can clearly see that there's no force pulling this guy outwards. It is just his inertia carrying him forward, and the floor he is walking on provides the centripetal force to prevent him from flying off. But what happens if our reference frame moves with the astronaut? This is called a rotating reference frame, or a non-inertial reference frame. To him, the rest of the world is moving, and he is standing stationary. In this reference frame, centrifugal force is absolutely a real and measurable force, pushing him downwards just like gravity. The only thing that is fictitious is his perception of what is causing it. This occurs because in physics and engineering, we must balance forces. The system has to be in equilibrium. Newton's third law states for every action there's an equal and opposite reaction. So if centripetal force exists in this reference frame, there has to be a force pushing him outwards. That is centrifugal force, and the moment the rotation stops, it vanishes again. So if this works so well, why haven't we seen a spinning space station yet? Well, one problem is size. To make this practical, we need a massive ship, which would be incredibly expensive to get into orbit. The acceleration your body will experience is directly proportional to the speed and radius of the space station. We can calculate the gravity Space Station V from 2001, A Space Odyssey would generate with some pretty simple math. The Space Station V had a diameter of 300 meters and spun on its axis once every 60 seconds. That would put its gravity at about the same as the Moon's. For it to have a gravity similar to Earth's, it would need to spin once every 24 seconds. If we were to make this a realistic size, let's say the same as the International Space Station, it would need to spin once every 10 seconds. This would probably be pretty disorientating. Just ask Sandra Bullock. Another problem we face on smaller stations like this is the gradient in acceleration you would experience. Because the acceleration is directly proportional to the distance to the rotational center, your head will experience less artificial gravity than your feet. This would force the blood to your feet, just like when you spin a bucket of water around. This effect diminishes with larger stations, so to make a practical space station with artificial gravity, the station would have to be huge, which is simply too expensive. Besides, the ISS is most valuable to us as a laboratory to test the effects of microgravity. But what if money was not an issue? What would it take to get a space station like Elysium, built for the mega-rich as an escape from the turmoil on Earth, into orbit? Elysium dwarfs Space Station V, measuring in at 60 kilometers wide, and it is estimated to weigh about 1 million metric tons. SpaceX can currently launch a kilogram into space for about $2,700 with their Falcon 9 rocket. This will be reduced to $1,650 per kilo when they launch their Falcon 9 Heavy variant at the end of the year. But it would take over 18,000 launches to bring the 1 million metric tons to low Earth orbit. That's $1.65 trillion to just get the materials of Elysium into space with current technologies. Then we have to worry about the cost of materials and engineering that would go into building something of this magnitude. That is far more difficult to calculate, but we can take some clues from the ISS. It is estimated to have cost about $150 billion in total. It took 36 shuttle flights at a cost of $1.4 billion each to bring the materials into space. That's a total cost of $50.4 billion. So the launch costs were just 33% of the total cost. A conservative estimate for the cost of Elysium could put it at $5 trillion. That's 62.3 Bill Gates. But there are 500,000 people on board Elysium, so if the costs were split between everyone, that would be about 10 million each. That isn't so far-fetched, and the price of space travel is destined to reduce in future. We do have materials strong enough to build a structure like this. The forces on Elysium would be similar to the ISS, other than the additional stress created by centripetal and centrifugal force. It's interesting to note that the designers of Elysium took note of this. The stress in spinning structures like this would decrease as you move away from the rotational center. This means it would need a stronger structure the closer you get to the center. This clearly influenced their design with these tapering spokes. But we run into some problems when we realize there isn't enough aluminium in the world to build this thing. It would take at least 10 years worth of the world's total aluminium production just to build the structure. This would cause a huge surge in the cost of material. An alternative method could be sourcing the materials from space. This could reduce the launch costs, and there is plenty of metallic material available on the Moon and near-Earth asteroids. So this technology is definitely possible. Our only barriers are launch costs and material availability. Something on the scale of Space Station V would be easily achievable. Who knows, maybe we'll be travelling to space as tourists in the near future. Once again, thanks for watching. I have a little bonus for you at the end of this outro. You can skip ahead or wait to watch it. I'd like to thank my Patreon supporters, Bastian, Nick and FG, for helping me to revise this video. Your support is really appreciated. Thank you. If you'd like to see more content or support Real Engineering, the links for my Patreon, Instagram, Facebook and Twitter accounts are below. So I promised to include this in my last video, but I couldn't figure out a way to include it in this video in a seamless way. The centrifugal governor was used in the Industrial Revolution to control the amount of steam entering the steam piston, which was essential as supply and demand can vary with fuel and load. For example, if the engineer puts more coal into the boiler, the pressure will rise and these masses will spin faster, which increases the centrifugal force and pushes them outwards. This raises this sleeve up, which in turn closes the valve to reduce the amount of steam entering the engine. So the centrifugal governor acts as a sensor to provide direct mechanical feedback to control the speed of the engine. It is one of my favourite inventions of the Industrial Revolution. Thanks for watching till the end, everyone. Hope you liked the video and feel free to ask me any questions on Twitter.